So I'd like to do just a slight review of where we are and what happens next. In particular, in material laws, is what we're going to look at today, and then starting next week, electrodynamics. That means optics, lasers, joule heating, things of that sort. So, where we are right now is we started in the very beginning of the semester with this idea that we had some kind of gadget, widget, robot, something of the sort. We went through an analysis, which you got in project number one, which was relatively coarse, but it gave you a taste of exactly how such a thing can be programmed. What are the machinery that are needed in terms of computational tools? One in particular, this genetic and genomic type optimization, is a relatively useful one. And it provided us with at least a course kind of behavior on exactly how we get materials into a certain location. But what we realize is that if we really do a deep dive on exactly what's going on with any of these processes, and the robot is a paradigm that's a good one for us to grasp onto, but it could have been some other kind of material handling or some other form of advanced manufacturing. We clearly need to know a little bit more about what goes on when you take some kind of raw piece of material and you project it or move it or deform it and you turn it into something useful, like, for example, in this case, something coming out of a printer and then becoming a splat, and then, of course, curing and solidifying onto a surface. That's probably a pretty good idea to work with. So we've been working with that for the last 2 weeks. And when we went into the deep dive, we had basically three or four different big topics. The first one was deformation, which is just purely kinematics. Uh, you should feel comfortable with the idea of the current configuration, the reference configuration, the idea of a displacement, the deformation gradient, the Green-Legrand strain, the Jacobian density in the current configuration or deformed configuration, and density in the undeformed configuration. I think you should feel comfortable, hopefully, after assignment number two with all of that. Then we have also the concepts of stress emanating from the balance of linear momentum. And one important concept here is the idea of the Cauchy stress, which is the actual stress per unit or force per unit area. That, of course, when multiplied by the normal, and let's write that also here on the side, is going to be able to give us the surface tractions, which comes up all the time in computational mechanics, manufacturing, pure and theoretical mechanics. So it's important to understand where this came from and what were the assumptions behind it. So you should feel comfortable also with the concept of a stress box, meaning a piece of material or a pneumatic, a mnemonic, sorry, of exactly representing what the stresses are on a single point inside a continuum, and this concept of what we put a little box around some point, and then we have, of course, surface forces surrounding it, and that in fact leads to this concept of the stress tensor, which is just simply nothing more than a matrix that collects up all of the values that we have on the surfaces surrounding that point. There's also the volume forces per unit, or forces per unit volume, the density and the current configuration, and of course the time derivative of the velocity. So that's the classical equation of the balance of linear momentum. And what we realized is because that thing is posed on a deformed configuration where it might not be easy to know beforehand where that configuration is, oftentimes we'll rewind the movie and go back to the original starting configuration, which is shown here. And the starting configuration, we formulate the differential equation there. If we do that, we get a slightly different differential equation that has similar form, but it now has this quantity called the second Piola-Kirchhoff stress, which is related to the Cauchy stress by taking 1 over j f times s times f transpose. We can get then the s, we multiply that by f, we take then the derivative or the gradient with respect to big X. Notice the difference between that and little x. We have the volumetric forces that are scaled by the Jacobian that also comes out of the transformations in the calculations. We have the original density, and then we have the time derivative of the velocity. So there's pluses and minuses. This, of course, is posed over the reference configuration. This is posed over the deformed configuration. Depending upon what we know from one state or the other, you should feel comfortable with utilizing either of both of these formulations and understanding where they came from, where they're applied to, and then depending upon the simplifications that one might have, you'll get different formulations and you might find it more advantageous to use one formulation or the other. One thing to make very clear here is they are equivalent. These are exactly the same statements of the balance of linear momentum. It's just that one is over the deformed configuration and one is over the reference. By the same token, last class period, we talked about the fundamentals laws of the first law of thermodynamics, sometimes known as the power equation. And the idea is that we isolated a little control volume called omega. We went through some calculations and we found that the governing differential equation over every point inside this body is given by the following term. It simply says that you take the energy stored in the at every point in the material, you take its time derivative, so that has units of power per unit mass, you multiply that times the density. You have this is equal to the inner product of the stress and the gradient of the velocity, the divergence of the heat conduction or heat flux Q, and then of course the density multiplied times the source per unit mass. The units for this are watts. That's very important to understand. This is watts per unit volume. So if you're thinking about what this equation represents, keep in mind when we derived it where it was a bunch of terms that were in here times a differential volume, little d omega, was equal to 0, and all of this was in watts. So this term here, which is all of the stuff that appears in this differential equation, is multiplied times a differential volume. Therefore, if this is units of volume, and this, we don't know what the units are, and this equals to watts, clearly if we divide by volume, whatever was inside of here has units of watts per unit volume. So that's critical to understand exactly what the physics are telling you here. By the same token as before, when we look at these kinds of simulations or these kinds of formulations, oftentimes what we'll do is we'll rewind the movie for the deformed configuration here and rewind it back to some initial undeformed configuration just like before. If we do that, we get a differential equation that looks like this. So it is the analog of exactly having the current configuration here and then the reference configuration formulation for balance of stress. We have the same thing for thermodynamics. We basically have a formulation that says take the original density as opposed to the current density. You take the energy per unit mass, and then its time derivative. That's the same term there and there. But that the inner product of S times E dot takes the place of sigma times grad V. It doesn't mean that it's equal to it. It just simply means that if you were looking at the contribution of the stress and the deformation to the overall power in the reference configuration, this is the term that represents it. In the current configuration, this is the term that represents it. We then have the divergence of the heat conduction. And of course, we have the value of the heat flux. The heat flux in the current configuration is Q, and in the reference configuration, it's Q0. I suggest that you look into the notes as I asked you to go through the derivations to understand what the differences are between Q0 and Q. They're very minor. They're just simply, one is the product of F times Q times the Jacobian, and it comes from this whole concept of the Nansen formulation. So Nansen, of course, is representing how things are balanced back and forth between those different configurations. Finally, we have the density per unit mass, or the mass per unit volume, which is rho 0 in the current or reference configuration. Then we have, of course, the source per unit mass. So you should feel at this point comfortable with these two formulations. And assignment number 2, which is the one that has been sent to you a while back by Brian, basically has that formulation there, which basically then is going to sort of give you a deep dive into all of these kinds of concepts to make you feel a little bit more comfortable with them. So what we have not finished off is this whole idea of the constitutive laws, and this requires quite a bit of discussion, and that's what we're going to discuss today. Before I go on, are there any questions before we dive into our next topic? All right, I will get right into it. So we are looking basically at the final part of chapter number 5. And in chapter number 5, we basically have the following. We have a idea of a constitutive law. A constitutive law simply ties the deformation to the loads applied. So depending upon what we do as the description, this could be at the atomic scale, it could be at the microscale, mesoscale. It will depend upon what our objectives are. Oftentimes, the way we approach this is we'll put some type of a strain gauge. It will measure the elongation in a selected area of length, usually called the gauge length. And then we'll basically track from piezoelectric signals. Typically with strain gauges, that's how it's done. And these electrical signals basically then get fed into some type of digital to analog readout, which then tells us roughly what the stress is versus what the strain is. Our problem is going to be the concept of stress and strain is not necessarily always linear. It's going to obviously depend upon how extreme the deformations are, and that's something we need to discuss today. The main concepts are going to be initially when we go through the analysis, we will find out that there's a very simple constitutive law that is sometimes referred to as Hooke's law. It is basically stating that the stress is related to the strain by a collection of material constants, usually known as the elasticity tensor. If we write it out in matrix form, so this is the compact tensorial notation that you'll see in the literature. If you write it out, however, in practical terms, usually the way this is written is that it is the stress, which is a 6x1 vector, because you don't need to take all 9 components since the stress is symmetric, meaning that sigma 1 3 is equal to sigma 3 1, sigma 2 3 is equal to sigma 3 2, sigma 1 2 is equal to sigma 2 1. Therefore, a more compact notation is to represent it in a vector-like form. We do the same thing for the strain, and if we find out that this is a 6x1 vector on this side, this is a 6x1 vector on this side, we either have 2 choices. Since we have to have a 6x1 vector on the left, either this entire matrix is just simply a 1x1 matrix with one material constant. That actually was tried very early on in the beginnings of mechanics. That didn't work out so well. Little by little, people found out there's just not one way to or not one constant that represents the rich behavior of materials. So then we're left with a choice. It's either going to be 1x1 or 6x6. And it turns out that 6x6 is what you need because you have to have the vectors equivalent on both sides. So going through a relatively complex set of arguments, and that's not the purpose of this class, is to go through the concepts of elastic symmetry, which I just show you here in section 5.62 by for completeness. You can go through several arguments that show that atomically how the lattices line up and how the elastic crystals line up. You can replace these material constants with several possible representations depending upon the degree of anisotropy of the material. So basically, anisotropy is a concept that basically, let me write as we're talking, basically states the following. If I have a piece of material and I come along and I isolate a little section of it, if I were to pull on the piece of material in different directions, depending upon the directions I pull into, the responses will be different. However, in the unique case, which is very prevalent in many forms, branches of mechanics and so forth, the material roughly behaves the same when pulled in all of the different directions. And that's simply because the underlying microstructure of the material is amorphous or random or statistically not biased in any way. Therefore, if the material has the same response in all of the different directions, we anoint that material as being isotropic, of course, from the Greek term of iso, meaning everywhere, and tropic, meaning direction. So it simply means that the material has the same response in every single way we pull it. And that can be proven mathematically by essentially these concepts of elastic symmetry. And if you're interested in those concepts, I can give another lecture about that a little bit later. It's a very rich and beautiful subject, but if you're interested in this topic, the class 127 or 227 are definitely the classes for you, because those deal with composite materials, especially fiber reinforced composite materials, which is not the subject of this class, but we'll touch upon it a little bit later in the semester. So the main point is that depending upon how many angles of elastic symmetry they are, so for example, if we look at a piece of material and we pull on it in one direction, like shown here, and then I pull on it in this direction and they have the same properties, sometimes that's referred to as an orthotropic material. If we then start to pull on it on one or two other different directions, then they seem to still give the same responses. With every single level of how many responses can be replicated in different directions, the degree of symmetry of the material starts to become greater and greater and greater. And as I said, in the limit, when the material becomes completely symmetric in all the directions, or same in all directions, we can represent this material as a so-called isotropic material. Isotropic materials have two material constants that need to describe every one of the 6 components in the constitutive law of the elasticity. The two that are most common in the scientific literature are the bulk modulus and the shear modulus, and there'll be some reasons for that, as we'll see later on today in class. But they primarily represent the shearing response, which is represented by the value of mu, and the bulk response, which is representing the amount of volumetric compression that a material has. So once we do that, there's several possible things that we can measure. And the things that are important are, for example, the pressure in the system, the deviatoric stress. Those will be related by these material constants. We also can bring in the concept of the Poisson ratio, which tells us how much a material contracts when being pulled in a certain direction. And then there are also the concepts of the Young's modulus, which we all know, but we'll review anyway. And then also the so-called Lamé parameter, which is given by the symbol lambda. So all of these different material constants are represented or related to one another in a variety of different ways. Of course, constitutive laws are not unique just simply to elasticity or mechanics or mechanical type of properties. We also have constitutive laws, for example, for diffusion. And many of us know that from our studies in material science. We have the so-called diffusivity tensor, which is similar to a conductivity in many regards and has some strong analogs to problems in thermal conduction. We'll talk about that a little bit later also in the semester. So that would bring us to the end of what the materials part is. And before now I do a deep dive on this, because I'd like to go in depth into several of these concepts. I'm curious about, from those of us that are online right now, have you seen the so-called generalized Hooke's law before? So let me flash it up on screen. What I'm saying is equation 5.41. Is that something that most of you have seen is in your undergraduate mechanics classes? Because that was one of the prereqs in the class, but I realized that, you know, each different mechanics class as an undergraduate may be different. So can I get a thumbs up or a thumbs down or something if you say, no, wait, slow down a bit. This looks like something completely alien to me. I see Muhammad is saying yes and Daniel is saying yes. Okay, Viana is saying no, good, okay. Any others? I'll assume that we kind of know it a little bit, but I'm not going to, you know, go very fast. I think it's an important concept enough that we need to have a pretty good handle on it. So if you could have chapter 5 kind of handy, we'll start with linear constitutive equations. And the idea here is first, we're going to basically do some soft walking before we start to gallop quickly into all the different material laws that are possible. So here is our basic issue. Whenever we pull on a piece of material, for example, let's say a thin sample usually is given something that looks like this. It usually has some grips on each of these sides. I'm just going to show it as a gripper. The gripper is going to pull the material in different directions. And then basically what we're going to have is we're going to have some kind of a strain gauge that is essentially going to read out pieces of information as the area here starts to deform and change. And usually, of course, the sample is given as a very large base here in the beginning because we don't want to bias the material from the grips. So we try to minimize the effect of the grips here and here by having a relatively large base. And then we have a small, thinner piece of material that's where we want to concentrate our description of the material law. Now, typically what we will see is we'll see something that says there's going to be something that is elongating. So there's going to be some kind of elongation and there's going to be some kind of a force. Now, depending upon how fancy you get, these elongations could be in the forms of strain or it could be some other measure. And the concept of force could be anything from the second Piola-Kirchhoff stress, which was the thing we've introduced all of last week, or it could be the Cauchy stress, but there's going to be something that's going to post-process force to usually become force per unit area. And it might be the current area, the actual area that's being deformed. It could be a reference area, but it'll be some type of normalization in this regard. And the elongation will also be some kind of percentage difference of the original length and the current length normalized by the original length. So it's going to be some type of non-dimensional number. And those two things then of stress, which is usually going to be newtons per meter squared, versus some type of dimensionless, let's call it meters per meters, just to give it some units, but of course it's dimensionless. We'll see some kind of readout that usually looks like this. The slope of the readout is usually given by a parameter EY. They all invariably start out linearly at the very, very small infinitesimal scale. And then depending upon what happens after this point, it could become metallic-like, it could become biological-like, it could become cementous type and then break. Everything after this point depends upon what happens in the microstructure. So, but the starting point of all of these are always going to be some kind of linearly elastic material law. Now, let's review how we could get to these linear elastic material laws. If you look at the panel on the left-hand side, what we want to do is first start with the first law of thermodynamics. So let's take a look at this. Let's write out that we have rho zero times W dot. We know that from the first law of thermodynamics, that's the stored amount of energy. And that's equal to, in this case, the second Piola-Kirchhoff stress multiplied times the Green-Legrand strain's time derivative. And then we have all this other stuff. We have divergence of Q0. We have also rho zero times Z. And what we're going to do is we're going to ignore all this stuff, the heat conduction, the sources per unit energy, we could care less. So we're just going to toss these and just concentrate just on the mechanical part first, okay? So if we concentrate on the mechanical part first, when the strains are super small, meaning we're here right when the material is about to deform, so right here at the super infinitesimal scale, we realize a couple of things actually occur. Number one, the second Piola-Kirchhoff stress is equal to the Cauchy stress because we know that they're equivalent at very, very small deformations. So in fact, we can rewrite this as sigma, that is the actual stress. They're immaterial, second Piola-Kirchhoff stress or Cauchy stress, they're one and the same at the smallest scales. And the Green-Legrand strain, which is this thing, recall, it's equal to 1/2 F transpose F minus 1. We realize that that thing in the limit becomes the small strain tensor when the deformations are small. So in fact, this becomes sigma times epsilon dot. So that provides a very important piece of information because as we can see here on the left-hand side, essentially what happens is we can write the following. We can take rho zero W dot is equal to rho zero times dW partial of W with respect to epsilon multiplied times the d epsilon dt. This is actually the chain rule of differentiation. So let me write it a little bit clearer here, like so. And what we have is we have that this is equal to, according to the first law of thermodynamics, which is what's shown there, this is equal to sigma inner product with the d epsilon dt, which is in fact exactly what this relationship here is. Now we notice, because both sides of the equation have this d epsilon dt, that it must be that rho zero times partial of w with respect to epsilon is actually equal to sigma. That's a very important relationship. What it says is that if the deformations are really small and you take the partial derivative, in other words, the change in the stored energy in the system with respect to the strain, so you take the body and you just strain it a little bit, that's what the partial derivative with the epsilon means, and you multiply it times the density, out pops out the stress. That's a very powerful concept. And what that means is that this, so far, we've never even said what the material is. This has to hold for any material. So any material we have, if we take the deformation and we just deform it slightly, if we calculate the amount of stored energy in the body and we take its partial derivative with respect to epsilon, its sensitivity to changes in the strain, multiply times the density, we get the stress. Okay, so here's how we're going to use that concept. Basically, what that statement says, again, written here, is partial of W with respect to epsilon. So what that means is this is the stored energy per unit mass, and this is equal to sigma. And what we're going to introduce is the so-called concept of the stored energy per unit volume. So if I take the density and I multiply it times the stored energy per unit mass, I can rewrite this unit-wise as the stored energy per unit volume. This is sometimes called the strain energy, and you might have seen this as undergraduates. That is the energy, for example, that's stored up by springs, that's stored up by elastic bodies, but it is the energy normalized by the unit volume. So this is per unit volume, and this is per unit mass, the little w. We like the per unit volume. There's a number of reasons that over the years this has been the preferred measure, although we could probably rewrite everything in terms of this, but it's a little bit easier to simply absorb the density in the definition and just have a single symbol. So typically what we will usually write, and what you'll see in the literature, is partial of W with respect to epsilon is equal to sigma. That is a sacred relationship in mechanics, because basically what it says is if you take the stored energy in the body and you take its partial derivative with respect to the strains, you're going to get the stresses. Now, one thing that should bother you is W is a scalar. So this is a scalar, right? And epsilon is a tensor. So the first thing you might want to ask is, how can you take a partial derivative with respect to a matrix? Well, really what that symbol means is that if I take the partial of W, I'm going to take the partial of W with respect to each one of the components of the strain, because the strain tensor is actually comprised of little components, epsilon I and J. And so what we're doing is we're taking for every component of epsilon ij, what pops out of here is a component of sigma ij. That's really what this shorthand notation means. And we do this for I equals 1, 2, 3, and j equals 1, 2, 3. Hence, we have two things. We have the strain, epsilon 1, 1, epsilon 1, 2, epsilon 1, 3, etc. That's a 3 by 3 matrix. And at the same time, we have something over here, sigma 1, 1, sigma 1, 2, sigma 1, 3, etc. And they're both 3 by 3 matrices that are shown there. Okay. Now, what we need to do now is we need to somehow tie the relationship between the strain here and the stress here. We need to basically figure out how they're connected. So here's the dilemma we have as practical, engineers or scientists. We want to figure out, okay, on the one side we have sigma, and it's 9 numbers because it's 3 by 3. On the other side, I have this relationship for epsilon, and it's also 9 numbers because it's 3 by 3. So something has to connect the two together. Now, at first glance, we'll say, well, fine. I guess if I write this out as one ginormous vector, this would be sigma 1, 1, sigma 2, 2, sigma 3, 3, sigma 1, 2, sigma 2, 3, sigma 3, 1. And then I would have also sigma 2, 1, sigma 3, 2, sigma 1, 3. That's the extra piece. So that's 9. And then the same thing over here for the strain. Now, the matrix that would have to connect the two, since this is a 9 by 9, a 9 by 1 vector and a 9 by 1 vector, would be 81 constants. That's a lot of stuff we have to do, or measurements we have to make to relate 9 numbers to 9 numbers. But we're mercifully lucky. It turns out that because the stress is symmetric, that we have the case that sigma 1, 2 is equal to sigma 2, 1, sigma 3, 1 is equal to sigma 1, 3, and sigma 2, 3 is equal to sigma 3, 2. We don't need to, these last little pieces here. So in fact, this becomes a 6 by 1 vector, and this becomes a 6 by 1 vector. So 81 constants, because we have a 9 by 9 matrix, now gets reduced to a 36 a 6 by 6 matrix, because now we have a 6 by 6 matrix. So the first trick is, please exploit symmetry of the stress and strain. Don't waste your time redundantly measuring the stuff. So it turns out we can reduce immediately by over a factor of 2 the number of experiments that we have to do. Super important. So what we do then is we do a series of arguments. We find out, number one, well, a next argument to make things a little bit simpler is that W is the stored energy in the body. Okay. Now, if I were to make this a one-dimensional problem, that it was just a spring and I pulled on it with some value K, what would I restrict the values of the spring constant? So imagine I'm taking the deformation of the body, X, and there's an initial length, which is called X0. And if I take X minus X0 and I square it, I divide by 2 and I multiply it by K, that would be the stored energy in one dimension. Okay. Now, the interesting thing about this, and of course you could normalize it as well by X0, but it's immaterial for the example we want to do. What's the important thing that we have as a restriction on K? Can anybody tell me?
K is positive.
Yes, K's got to be less than infinity for sure. It's not an infinitely stiff spring, and it's got to be greater than 0. So clearly we have the restriction that if this is going to be a stored energy means it's greater than or equal to 0, and that W could only be equal to 0 in one case only, if and only if all of the strains were equal to 0, right? So in other words, if there was no strain in the body, the energy would of course be that's stored up in the body must be 0. It's just equivalent to saying if X didn't deform at all and it was equal to X0, certainly the stored energy would be 0 if they're equivalent, that would be gone. But any other case, we must have that the stored energy has to be positive. Now, I want you as an exercise to go through the examples in packet number 8. In packet number 8, we go through a series of arguments that show that the implications of this are that the stored energy being greater or always being bigger than 0 and only equal to 0 when the strain is equal to 0 is that the elasticity tensor, which is what we're going to introduce momentarily, must be symmetric, meaning that the elasticity that connects sigma, so sigma is this matrix, the elasticity is another matrix, as we'll see shortly, and I'm drawing 4 arrows for a reason, and that the strain, the relationship that shows something that ties the strain to the stress, we found out that the elasticity tensor has to be symmetric. Now, I want to make a very important observation here. When we write this relationship here, that sigma is equal to some set of material constants,
multiplied by the strain. We put 4 lines underneath here because it's what we call a fourth order tensor. What that means is that stress we know is sigma ij. It has 2 components, 1 and 2. The strain is also 2 components. We'll call those K and L. So there are 2 components here as well. Then there's something on the end that connects the two. It is epsilon I J K L. It is a matrix of all kinds of constants, but it has 4 indices. So it's not quite a normal type of matrix. It has 4 free things. So when we think about a matrix, right, what do we think a matrix has? A matrix has a row and a column. And the rows are given by I and the columns are given by J. So all the components are A, I, J. Now the problem is because now we want to relate one matrix here with 2 free indices and one matrix here with 2 free indices. They're not necessarily the same indices, that we have to have something that has 4 indices that ties them together. Explicitly more written out more formally is epsilon ij is equal to summation of I equals, or sorry, K equals 1 to 3. L equals 1 to 3, K equals 1 to 3. Then J equals 1 to 3. And then I equals 1 to 3. All of these material constants, E, I, J, K, L, are going to be multiplied times epsilon KL. That's a long and arduous process, and this makes things very difficult to write if we had to keep writing this over and over and over again, but we could. And as you see here on the left-hand side, that's how we first start out. But what we want to find out is, maybe there's a more compact way of writing this, and it's the technique that has been used for a variety of different years over the years, and it makes it very simple, primarily driven by one thing: finite elements and MATLAB. People like matrices. They don't want to necessarily write out every time they need to multiply something out with 4 summation signs. So what they do is they say, you know what, let's exploit that this is symmetric. So in fact, this is going to be a 6 by 1 vector, which is basically shown there as a vector here in the relationship somewhere along here. Let me see where it is. Just a moment, written it out. Yep, so it's a 6 by 1. Well, in fact, let me show it better on screen. So we have a 6 by 1 vector shown there. We have a 6 by 1 vector shown here. And what we basically do is we say, fine, instead of having all of these summations and having them summed up over everything going from 1 to 3, we're just going to write this as a 6 by 1 vector, and a 6 by 6 vector, and we're going to write the strains here also as a 6 by 1 vector. So this now becomes, in matrix notation, it looks something like this. We have all the components of the stress. We have all the components of the strain, and then we have this big monster here that is a 6 by 6 matrix, and each of the components we're going to call E with a little line in between it. So I draw it like this with a line in between so we don't get confused with the Green-Legrand strain, because we've already used that symbol for E. So at this point, we start to go through a variety of different arguments, and the arguments basically stem from the following. We essentially assume that, number one, this material has a certain type of elastic symmetry. I mentioned that before. This isn't the subject of this class, but basically it says if the material can deform the same way in this direction, and 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 so forth, we assume that the material is isotropic, and this constitutive law that connects epsilon with sigma can be written in a much more reduced fashion. And that reduced fashion basically looks like the following. And so let me write it here for you. We can rewrite the constitutive law in the following way. We can write this elasticity as kappa plus 4/3 mu, kappa minus 2/3 mu, kappa minus 2/3 mu, 0, 0, 0. Kappa minus 2/3 mu, kappa plus 4/3 mu, kappa minus 2/3 mu, 0, 0, 0. Kappa minus 2/3 mu, kappa minus 2/3 mu, kappa plus 4/3 mu, 0, 0, 0. And then 0, 0, 0, mu, 0, 0, 0, 0, 0, 0, mu, 0, 0, 0, 0, 0, 0, mu. Okay, it has a wonderful kind of form to it. Now, the nice thing about this is that that means that every one of the components that exists inside this matrix equation actually can be represented by a combination of two parameters, kappa and mu. The reason that we have this kind of kooky decomposition is that those material constants have a very physical meaning. Number one, kappa is the so-called bulk modulus of the material. Okay, so the bulk modulus of the material, as we'll see later, tells us how squishy a material is with respect to its volumetric deformation. The shear modulus of the material tells us how resistant it is to being sheared in different directions. So there's a nice decomposition that goes on there. But what's much more important is the fact that we have the following. When we write sigma is equal to E epsilon, that is equivalent to writing sigma equals to E as a matrix times epsilon, which is equivalent to sigma ij equals to Eij multiplied times epsilon KL. All of these types of representations are really one and the same. So the main point I want to come across is that depending upon the situation, the analyst might use any of these different representations interchangeably. Now, when the material is isotropic, we get some simplifications in writing all of this kinds of stuff. For example, when it's isotropic, we can rewrite this as 3 kappa times the trace of epsilon over 3 times the identity matrix plus 2 mu epsilon prime. It's kind of a thing that jumps up out of nowhere, but that essentially is exactly the constitutive law. When we write everything in terms of kappa and mu's, it can be written in this very compact notation that I'm showing you there. Now, there are a couple of reasons why this particular representation is important, and that's what we're seeing here at the bottom of page 5, which I would like to lead off from. Now, some important observations in this kind of a representation. Whenever we write the stored energy of the body, and we write it as epsilon inner product with E inner product with epsilon, the reason being is that the stored energy is the product of the stress multiplied times the strain times a half. Again, go back to your notes and see exactly that representation at the beginning of the packet. Since this is greater than 0, since it's an energy, what is the implication of that statement? In other words, if I told you, I've got this thing, it's called W, it's always bigger than 0, I can write it in this form, but I can write it, maybe this form is a little bit easier. I can write it as epsilon transpose, the vector form, multiplied times the matrix E, multiplied times the vector epsilon. If I told you this thing was always greater than 0, what's the implication of that statement? It's okay to guess. Brian, do you know the answer? Hello?
I don't exactly have the answer, but I do see this in like a weighted inner product sort of manner.
Yeah. Yeah, so I mean, let's back it up and ask, so I don't want to give you the answer outright. Let me do it a different way. Suppose I said I take a vector x and I multiply it times a matrix A, and I multiply it times a vector x, and I divide by 2, and I tell you this thing is bigger than 0 for all x. No matter what x is, there's a vector x, and I multiply it. So let me make it look like a matrix and a vector here. And I told you no matter what happens, the product of all that stuff is always bigger than 0 no matter what x is. How is that possible? What is the implication on the matrix A? You've seen it in linear algebra.
It's semi-positive definite.
It is positive definite. That is exactly right. So what that means is the implication that no matter how I change x, so if I take x here and I multiply it times this matrix and I multiply it by itself again, and no matter what those products are, it's always bigger than 0. The implication is that A is a positive definite matrix. Now, let's explore what positive definite means. If I take x as a scalar and I multiplied it by a value A and I multiplied by x and I divide by 2, what would happen if I said, you know what, all of this stuff is bigger than 0, no matter what the value of x is, any? What would you tell me about the number, the scalar A?
It's positive.
A is a positive number, right? I mean, there's no way if x is multiplied by itself, I'm really saying that ax squared over 2 is bigger than 0. Well, there's only one possibility. You know, x could be anything, but it's squared. A has to be, of course, bigger than 0, right? That's just algebra. It is the same idea when we take a vector, x transpose, multiply it times the matrix A, multiply it times x, divide by 2, and then we say also this is bigger than 0 for all x. Well, guess what? That means that A is bigger than 0. But A is a matrix. So what does the implication of A bigger than 0 mean? It doesn't mean that every single entry of A, so if A was a 3 by 3 matrix, it doesn't mean A11, A12, A13, A21, A22, A23, A31, A32, A33. That's what A is. What does A bigger than 0 mean in linear algebra lingo? In other words, if I tell you a matrix is positive definite, what does that mean? Can anyone tell me? Well, when a matrix is positive definite, that means that its eigenvalues of A are all bigger than 0, right? So what that means is if I take the eigenvalues of the matrix A, that the eigenvalues of A, let's call them lambda 1, lambda 2, lambda 3, are all bigger than 0. So now let's rewind and ask ourselves, when we have a matrix E, so we have this matrix E, and it's a 6 by 6 matrix, and I tell you that that thing is also greater than 0, what does that mean? there were 3 eigenvalues for a 3 by 3 matrix. How many eigenvalues are there for a 6 by 6 matrix?
6.
6. So the eigenvalues of E, if they're all greater than 0, means that every one of those guys, lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, lambda 6, all have to be greater than or equal to 0. So one of the first things that people do whenever they do experimental measurements, and they measure all of these 6 by 6 constants, and they come up with an elasticity tensor, one easy way to check immediately if the experiments are wrong or that there's been a mistake is they compute the eigenvalues of whatever they've measured. It's a very practical use of linear algebra. What that immediately says is if any of the eigenvalues are 0 or less than 0, someone has made a mistake in the measurements. So it's a very practical use for the ideas of linear algebra. It turns out, however, when the matrix has this kind of form, kappa and mu, and so forth, that the eigenvalues of E actually happen to have a very specific format. They are equal to kappa, 2 mu, 2 mu, 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 and mu. So it turns out that the eigenvalues, 3 kappa, are all greater than or equal to 0. What that means is that it immediately enforces that the bulk modulus and the shear modulus, since each one of these 6 quantities has to be greater than 0, because they're all eigenvalues, it turns out that it enforces that kappa must be greater than 0, and so does mu must be greater than 0. So the implication of this is extremely important. What that forces is that the bulk modulus and shear modulus of the material must always be greater than 0 or positive. Now, what we're going to find out is the bulk modulus tells us how, and I probably won't spell this right, how squishy the material is. So basically it tells us if a material starts out like this and squishes into some self-similar manner like this, that this tells us how squishy that material is. And then the material, depending upon if we shear it like this tells us the resistance to how shear deformable it is. So what ensues now in the next pages in packet number 8, is it talks a lot about exactly what are these constitutive laws and what do they look like. Now, for the sake of, I know this is a lot of information, I'm going to stop here today, but I want you to promise me that you are going to look at everything starting at the middle of page 5 and go through all of the algebra to understand what these material constants are, and we'll review those on next Tuesday. Then we'll start fresh and early with electrodynamics. So please go through the concepts here, starting on page or equation 560. This is where we've left off. Go through the analysis. It's very straightforward. It's only 2 pages long, but it's pretty dense, so it's probably easier to look at the packets. And then we will start with electrodynamics. So please hopefully read that also by next Tuesday. And then we'll start basically with a brand new section in our notes and so forth. But I wanted to get quickly to the idea of constitutive laws because you need that for assignment number 2. But this basically brings us more or less to the end of assignment number 2. And I don't know whether Brian wants to make any statements or clarifications on assignment number 2, but it's fairly straightforward. It is the concepts first of deformation, then the concepts of stress, then the concepts of thermodynamics, utilizing also the fact that we need constitutive laws, and a very simple one, of course, is Hooke's law, which we give to you also at the back of chapter, at the end of the assignment in equation number 12, which is exactly what we just saw there a moment ago. Brian, is there anything you want to add in terms of hints or help in that assignment?
I've been posting on
Piazza for anybody that has questions. And then I will also be holding office hours right after this lecture.
Okay, are there any questions on what I would like you to do for next class period? Basically, I would like for you to look at everything starting at the middle of page 5, carefully understand, what an isotropic constitutive law looks like, and then be able to work with the material constants, lambda, epsilon, kappa, and mu, understand what they're used for. And then what we're going to do is we're going to look at things like material failure and understand exactly how these constitutive laws relate also to the concepts of when a material ceases to become linearly elastic. Okay? Are there any questions? All right then, have a good weekend, and please don't hesitate to reach out to me for discussion, but I will assume by next Tuesday that you're up to speed and have gone through packets 1 through 8, obviously. And then please prepare yourself for electrodynamics. That's a little bit more complicated, but it will be very fruitful complications because we'll be able to use all of that stuff to identify how materials respond to electromagnetic fields, which of course is a key component in much of the material processing literature that's out there in advanced manufacturing. Have a good day, and I will see you next week.